Okay, the clock on here now says 9:30, so we'll start. First of all, are there any questions about anything on the homework? Okay, yes.
So in the first question, or in the second one, we are asked to rank companies according to what we feel like is a good measure to rank them.
Right.
Now I don't exactly remember the question, but there were the things like some companies like WLTW and FTV, they have their dates as well as along with the timestamps mentioned, right? So it's date and time in the date column of prices.csv, and the other companies, they don't have any timestamps mentioned, but they just have their dates mentioned. So when I try to filter the data, these two companies are something that are not being able to get filtered out because of the extra timestamps they have. So I even looked a little about it. So basically, if we do pandas and data frame, if we use it to extract the timestamps, then it will convert it to not a time automatically, and the errors will be covered. So like I'm not able to filter these two companies out because of the extra timestamps they have.
Okay, so here are a couple of different things in the question. So let me start with what I think I hear, and then if I'm wrong, I want you to correct me again. The first person is, what I want you to do in one of these parts is to order the companies by how interesting they are. And the reason for this is, okay, here's a question. I don't know how much people know about the stock market. How many companies are in the S&P 500? Okay, 500. I think that's a little trick. I think it may be, for some reason when I do these things, I think it may be a little bit of a rounding error on that, but it's big O of 500. We agree. And some of these companies you have heard of, and some of these companies you haven't. And I think that it is good for your, to look at these things. If you have companies you care about, okay, it will look more like just random numbers than if you're looking at, the 495th biggest company, which very well you may never have heard of. So that's why I want you to rank these based on how big and interesting they are. Now, your question here was saying something, I think, that in this data set, there was some kind of an artifact where two of the companies in there had like an extra data field or missed a date field. Is that right?
No, so in the same date field, it has the date as well as the timestamp. So 0000, like exact midnight.
Yeah.
Is the timestamp. Okay.
Yeah.
These were the only two companies that I could see. They were not getting filtered out because I was looping through each of them.
Okay, so what I think you're saying, and again, correct me if I'm wrong, is that however the guy built this data set, on a couple companies, he or she left a timestamp, which they didn't on the other companies.
Yes.
And the question is, what do I do with it? Okay, could I throw these companies out? That's, I guess, part of what you're saying your pandas couldn't read it, throw them out. Okay, is there another way around this problem? Yeah. Okay, so you're saying coerce them into a date-time object, or I would say go through and delete the time field. Okay, that I can kind of imagine. I mean, and maybe I don't know if this is a too glib answer, so let me know. But if you're telling me that there are a bunch of records that were kind of scraped by whoever assembled this thing, and for some reason they scraped two of the companies in a slightly different way, one possibility might be to clean up the artifact that was introduced before you go and do your regular processing.
So I did think about it, but again the timestamps here were it's not much of significance here because it is exact midnight. But if there was a data set in which timestamps are of significance, then wouldn't it be wrong to delete the timestamp?
Okay, would it be wrong to delete the timestamp? We will talk about data cleaning, I believe, next week. It happens to be something I like, okay? But there is this question here of what should this is a good example of what is a cleaning problem, okay? The guy who assembled this data set did something dumb and left a timestamp in there for some reason, okay? And, what do you do with it? It sounds to me from what you're saying that this timestamp doesn't really convey that much information, and if so, then it should probably be dispatched, okay? But that's a question of understanding what it is and why it's there. So you guys figure it out. You're telling me if this, oh my God, this is, if it could be, oh my God, this is such an error. If we include these companies in any way, it will ruin all the analysis, okay? That these two companies are based on Mars, and in Mars they have a different time system, and it could be that it ruined everything, in which case you're right, dropping the company. It could be that this was a processing artifact, and that if you delete this column, it makes no, this field, okay, it makes no difference, okay, and then you can treat them all the way that you treat everybody else. And this is a judgment call. I'm not going to tell you one is right and one is wrong. This is why I want these assignments to be somewhat open-ended, okay? And again, the hope is over the course of the semester we develop better and better judgment, okay? Any questions? Any other questions about the homework? Okay. How many people have gotten started on it? See some twitching. How many people have not gotten started on it? Okay, I recommend getting started on it. Okay, because especially if your skills in Python and data exploration are relatively limited, okay, this will take longer than you think it will. Any questions? Oh, and one thing that I will tell you when it comes to taking longer than you think it will, okay, one principle for this analysis in this course, it's very important, is this phenomena called KISS. Does anyone know what the acronym KISS stands for? What was it?
Keep it simple, stupid.
Keep it simple, comma, stupid, okay, that means you, okay? It's important that when you're doing these things, you make I would say, make a quick pass through this, okay, and do something quick before but set up a pipeline so later you could optimize and fix something if you later have more time for doing it or something like that. So this question on the fields, okay, is a good example of this somehow. If he came and encountered this thing and said, oh my God, okay, my thing can do 498 of the companies, it can't do 500 of the companies, what should I do? Should I sit and agonize? Should I wait till I can ask professor in class? The answer is, what's the simplest thing to do? Probably it was to drop the other two companies, right? And you move on. And later on, if he now has an idea how to rescue them, he can go and fix this up later and come back and do that. So I strongly encourage people to make a quick pass simply through everything, rather than get stuck on making sure everything is right, or done with the greatest possible depth. Okay? Any questions about that? Any other questions about the assignment?
The prices and the adjusted prices, two tables are different, right? So what's the relation between these two?
Okay, so they say that there is a data set that is called prices, and there is a data set called adjusted prices. What is the difference? The difference is one of them is adjusted. Okay? Now, what does that mean? Okay? Again, there's this phenomena in stocks of stock splits, that when you have when you have a stock price that gets too high per share, companies to encourage more investors to make it seem more reasonable will instead take one of their old shares and divide it into 3 or 5 or 7 or 2 new shares. And they will take your old share and give you 3 new shares in exchange. Now what's the result? What is the change in value to you? Nothing. It's the difference of, I had a $10 bill. I give it to the bank, they give me 10 $1 bills. Am I richer? Okay? The answer is no. But if you now want to compare the price of the stock, what would happen if you look at the price of a stock when there's a split? Tesla's doing great, kabunk, right? Suddenly one day it divides by 3, okay? Is it that Elon Musk said something stupid and the company collapsed? Or is it a non-event in the value of it? It's really a non-event, right? The adjusted prices compensate for the splits. The raw prices don't, okay? And that's kind of what the series is. And so one of the parts of the assignment is discover where there were splits, okay? And this should be something you can do given the 2 series, okay? Any questions about that? You have to understand what a split is and how that works and how they're calculating it. But I claim that at that point you can do it. Any questions? Yes?
So what's an appropriate ratio? Because some companies do like really weird splits where they're like 100, like 1,000, 1836 to 1,000. So like it's like a 1.83 split. Is that considered a valid split?
Okay, if they split like that, then it's who am I to tell the New York Stock Exchange what a valid split is? Okay, it could be that they have ratios there that are, you're saying, not integral ratios. Okay, it could very well be. Okay, there's no reason you shouldn't be able to discover that. Okay, any questions? Sometimes when they do adjusted prices, there's other phenomena that are also captured in there that change, like giving dividends, but I don't know if that's in there or not. Okay? Any other questions about the assignment? Okay, I encourage people to get going, and I encourage you to discuss your questions like these. It's great to discuss them over Piazza so everyone can see. Any questions? Okay. So today, what I would like to talk about is correlation, okay? And that a lot of what drives things in data science is the analysis of correlations of variables. And we say that 2 variables, okay, x and y, are correlated when there is, the values of x have some predictive values of y, or equivalently, y has some predictive value for x, okay? And the correlation coefficient is a statistic that says that if you've got a bunch of x, y points, you've got n points, each of which has an x, each of which has a y, to what extent is y a function of x and x a function of y, okay? And what is the correlation coefficient? It ranges from a 1 if the 2 sequences are perfectly correlated. If I know the value of x, I absolutely know the value of y. To -1, which means that they are anti-correlated, meaning that whenever x is large, y is small. But still, they could be perfectly, they could be perfect predictions in them. What is an example of a pair of numbers? If I had to give you a sequence of numbers that are perfectly anti-correlated, what would be a good example? Okay, yeah? Positive numbers and positive numbers and the associated negative numbers. If I just give you, let's say, people's weight and people's bank accounts, you may have, or your credit balances may all be negative, your weights will all be positive. There still could be a very positive correlation there. But I think if you took a look at if I said your weight and -1 times your weight, right? The bigger your weight, the smaller the negative of your weight is. Does everybody agree with that? And if I know your negative weight, do I know your weight? So that would be an example of an anti-correlated function, okay? And 0 means that it's uncorrelated, that there's no relationship between the two that you can detect by the correlation coefficient. Any questions about that? So what is the most common measure of correlation? It's something called the Pearson correlation coefficient, okay? What is it doing? It says basically if I have for every one of my n xy pairs, I take x of I minus the mean of the x values times y of I minus the mean of the y values, okay? And I sum this up. Now this thing on top is something we will call the covariance, okay? And so sometimes that's an interesting statistic. What is interesting about the covariance? It means that if I have a value x that is bigger than the mean, okay, this difference will be positive. If y is also bigger than the mean, then the yi minus the mean will be positive. If both of these are bigger than the mean, the covariance term makes a positive contribution to the correlation coefficient. The covariance is hot, you add something in this sum to the covariance when both xi and yi are bigger than their means. What happens when they're both less than their means? Okay? If x of I is less than their mean, x of I minus the mean is going to be negative. yi is less than the mean, this is going to be negative. Negative times negative is positive, right? So if they are both small relative to their means or both big relative to their means, this makes a positive contribution to the, the covariance. On the other hand, what if these numbers are kind of out of phase? Where x is bigger than the mean, its mean, and y is less than its mean, we get a negative term. What would we expect if x of I and y of I have nothing to do with each other? The chances that both of them are either big or small is about a half. And the chance that one of them is big and one of them is small is a half. So you would kind of expect these terms to offset each other in the sum, and you get to something that's towards 0. Okay? So this is why if there is a positive correlation, we expect the covariance big. If there is a no correlation, we expect the covariance to go to 0. And if there's an anti-correlation, that means whenever this thing is big, this thing is small. You would expect it to go to a very negative number. Any questions? The bottom part of our correlation statistic is basically talking about we take the sum of the squares of the deviations. This is something that shows up in kind of variance calculations. Remember we talked about variance? This looks like a variance term. A square root of a variance term looks like a standard deviation. So this is saying basically if we take the covariance and normalize it by the standard deviation of the x values and times the standard deviation of the y values, it turns out magically this comes down between -1 and 1, and this is our correlation thing. Any questions about what this means? Yes?
You actually told that the correlation coefficient will be closer to 0 if x and y are not related, right?
Yes.
Can you repeat that like twice?
Why is it? Okay, so let's think about it. If you want something, if you're adding a bunch of numbers together and you want them to go to be 0, how do you do it? Okay, one way to do it is to make all of them terms 0, but that's a boring way. A smarter way, or a better way would be if you're adding a bunch of numbers together and the sum of the positive terms equals the sum of the negative terms. What's going to happen here if x of I and y of I are kind of random permutations of the values? So there's no association between the x's and the y's. Okay? A quarter of the time, you're going to get an XY pair where X is greater than the mean and Y is greater than the mean. That's going to mean a positive thing times a positive thing, or a positive thing. A quarter of the time you would get something X less than the mean and Y less than the mean. This would be a negative number times a negative number, which is positive. So half the time half of these terms we would expect to be positive, and half the terms are going to be negative, where one is above the mean and not the other. And the other, and so we're summing up n terms, half of which should be positive, half of which should be negative. That should be 0. Any questions about that? Good. Now, how do you interpret peer correlations? I looked up a couple of things, at one point, a couple of correlations to get an idea of what are the strength of kind of correlations you see in the real world. Now, the first one is kind of an easy one to kind of see how you do it. SAT scores are the kind of undergrad college exam, okay? That measure the high school exam you take to decide whether you should go to, what college you should go to as a first approximation. And there's freshman GPA. You would like to think that of all the people admitted to Stony Brook, some have higher SAT scores than others. They're supposed to be better students. They should get better grades. Is this true? Well, in one study I saw that the correlation between SAT scores and the first year GPA was 0.47. Is that a positive correlation? Is it a strong correlation? You say no. I mean, it's pretty good. I think that, I'm not going to, part of me wants to embarrass everybody by asking them your entry scores and see what your grades are like. But generally, I think that the people, this is a non-trivial correlation. Okay, we'll see what does it mean actually a little bit later. But this is when you see a correlation like 0.47, that's a pretty high correlation on things you see. Okay, it's not unbelievably high. Now there's some other correlations. Suppose you correlate the SAT scores that a kid gets and how much money their parents make. Okay? These are two numerical series. You can correlate it. And in the study I saw, the correlation was 0.42. Okay? That's almost as strong as with the grades. Should we admit students based on how much money the parents make? Some people will say yes, okay? But a lot of people wouldn't, okay? It may be simpler to do it that way, okay? But it does show that, it tells you something, okay? What were other things? Here I said the correlation between income and coronary disease. Now, if you think about when you see a statistic like, wow, that's negative 0.7, what is actually being correlated here? Okay? You have to think a little bit about this, okay? Does it make sense to do this correlation? Income is a number. I can kind of believe everyone here has an income. Does everybody have a coronary disease? How much coronary disease you have? So what is it actually, kind of correlating to on the other side? I think this is kind of by region, that if you have every state or every county, there's an average income and there's a certain prevalence of how many people in it have coronary disease. And so that's what I think this is correlating. But what does a correlation of negative 0.7 mean? It means that as a negative thing, that means what? That means that the richer a county is, what happens to their coronary disease? Goes down, okay? Why is that? Well, maybe they have more money for health care. Maybe they eat better. I don't know why that is. Maybe it's a coincidence, although this is a pretty strong correlation, right? Similar study between smoking, I think, and this was also done on the basis of countries, I think. The smoking rate and the death rate. Here this is positive, okay? Strong positive, okay? What about video games and violent behavior? You might imagine that you break, people and students into cohorts based on maybe for every, how much the time they spend watching video games, and then how much crime is committed by these people. Okay? So in this study, again, you have to be careful what were the two numerical variables before you quote it. But this one I still claimed a rate correlation of 0.19. Is that a strong correlation? You say no. Is it a real correlation? Well, we have to figure out what that means. I mean, that's an interesting question. If it's a real correlation, maybe we do something about video games, right? Okay? So anyway, the correlation coefficient gives you a metric to start to ask questions about what, how strong is the relationship between two variables. Any questions? Now, one way to interpret the strength of a correlation, okay, or the kind of right way to do it, is to talk about the R squared. What is the R squared? That is the square of the correlation coefficient. Okay? What does the correlation coefficient range between? -1 and 1. What does the square of the correlation coefficient range between? 0 and 1. Okay? Now, what is the case? For either -1 or 1, if you have a correlation of that strong, it is explaining everything. Okay? Now, when you talk about an R squared estimate, okay, that gives you a number between 0 and 1. And the importance of the R squared estimate is that it estimates the fraction of the variance in Y that is explained by X in a simple linear regression. Okay, let's think what this means. Okay, so first, let's say that this is true. If it's an R squared is our measure of the strength of a relationship, okay, it means that the, that the kind of importance, the predictive value of a correlation decreases by a square. Weak correlations have very little predictive power. High correlations have less predictive power than you might think. So let's take a look at an example. You guys know that you have heights and weights. The correlation of height and weight is about 0.8. Okay? If somebody's tall, do they weigh more than somebody that's short? Almost certainly. Okay? Could there be an incredibly skinny tall guy and an incredibly fat short person? The answer is yes. But what does it mean? The square of 0.8 is 0.64, right? And that says that kind of 2/3 of the variance in Y is explained by, 2/3 of the variance in weight is explained by height. Okay? That's the way to interpret it. Okay? Any questions? Yeah.
Can you please repeat it about the variance? I didn't get it.
Okay, let me show an example, or let me show this one more, explain this in this variance issue a little bit differently, and then let's see if there's still a question. Okay? Suppose we have a value x here and a value y here, and we have points like this. Does everybody see those points? There looks like a pretty good correlation between the x value and the y value here. In this case, I believe it was a 0.94 correlation between these. What is the variance? If you have a set of points here, and you talk about the variance, okay, notice that the variance, remember, was what? The sum of the squares, basically, of the differences from the mean, right? Now, if we're looking at the variance in the y's, suppose the y value was height, okay? And suppose you measured somebody's height in centimeters, and you measured somebody's height in feet. Do you guys understand feet? You're in America now, right? There's feet, okay? We use feet to measure things. Which is higher? Your variance of people in this room measured in centimeters, the height of these people in the room measured in centimeters, or the people measured in feet? Centimeters, right? Because again, the numbers are bigger, the range of the numbers is bigger, right? So in this case, you would get a similar picture properly scaled if this y was measured in feet or meters, or centimeters. The difference is what the range of numbers is, right? So anyway, what do we now do? Suppose we now fit a regression line through this, okay? The best line that goes through these points, okay? That says, what is the value, the line y equals mx plus b. X is the x variable, m is some constant, is the slope, b is the intercept. And now we take the residuals, the values y minus the value of this predicted value for x. Okay? What is going to happen after we take the, we now take y minus the regressed value as a function of x? Does everybody see now we get the same number of points? The number of points are roughly, half of them above y equals 0, half of them are below y equals 0. That makes sense because y was trying to predict what the values were. If it's got the best possible fit, probably half of them are above, half of them are below, roughly, kinda. Okay? What do we know now about the variance of the residuals? What's going to be true about the variance of the residual values here, the y's here, compared to the y's here? Okay, what do we think the variance is going to be different? Which is higher variance, the original points or the residuals? The value where instead of using plotting y, I use y minus the value of the regression line. Again, let me make sure people understand what I mean by residual. Suppose this is my regression line, and suppose I have some point here. This is what the x is, this is what the y is. What is the residual? It's the difference between what the value of my regression line is for that x and the y value from that. This is the residual. Okay? What do we think about the residuals? What is going to be the variance of the residuals relative to the original ones? Someone with a hand. Okay? Yeah? The residuals, if x meant, if there was any kind of a meaningful correlation between x and y, the residuals are going to subtract out that relationship, right? And so what remains should be smaller, right? It's got to be smaller. And so if the range of numbers is smaller, we would expect that the the variance in the residual is less than the original. So what does it mean? In general, as we generally speak, if we have a correlation of r, 1 minus r squared is going to be equal to the variance of the original divided by, the variance of the residuals divided by the variance of the originals. Okay? Any questions about that? Let's think that through. What happens if there's a correlation that is perfect? Suppose that there is a perfect correlation between x and y. What do we expect? What's r going to be? 1. What's 1 minus r squared? 0. What's the variance of the residuals going to be? 0. If everything is explained, if your weight is perfectly displayed, determined by your height, once I subtract out that relationship, there should be nothing left, right? So in this case, if there's a perfect correlation, then we would expect that this would go away. What would happen if there was 0 correlation? What would be the case? What is r going to be? What is 0 squared? 1 minus 0 squared is 1, right? If there is no relationship whatsoever between x and y, if I find the best fitting line between them and subtract this thing out, will I have improved matters in any way? No. Let's say, what are two things that wouldn't have any correlation with your weight? Let's say the last digit of your social security number, right? Could I, if I tried to use the last digit of your social security number to compute your weight, okay, I would have no information to do. I would come up with some kind of a line, okay? It shouldn't reduce the variance at all, okay? So this is the nature of the definition of what's happening here. Any questions? Okay, and what is it that explains this thing? What is this remaining y minus the residual? What are those points now that you see there? Every point is a person, right? This is going to say what is their weight that is not explainable by their height, right? What could be captured in that residual? Maybe how much they like to eat, how much they like to exercise, how much, whether they, things like that, okay? Any questions? Okay, good. Now, in general, there is a useful statistic here for any kind of a predictor, to evaluate any kind of a predictor that you do. Which is, they call it the coefficient of determination. What if we took the sum of squares error of a, let's say you want to try to predict somebody's weight from variables. You have their height, you have their, maybe how old they are, maybe you have their eye color, all kinds of statistics about them. Okay, and you want to try to predict their weight. Now, in linear regression, we would let f of x be a linear function of these variables. But suppose you have an arbitrary function. You use a neural network and you say, I can predict these things. How good is my neural network? Well, there's this notion of coefficient of determination. The RSS is the residual sum of squares. What is the sum of squares difference between the actual weight and my prediction by my fancy method, not just linear regression, whatever I want? Okay? You could look at what is the sum of squares of the residuals divided by the sum of squares deviation of the originals. And if you have a good predictor of weight, then this coefficient of determination is going to be kind of more extreme. Okay? Any questions about that? Okay, so does everybody see that although we define for the purposes of minimizing variance, how do we interpret a correlation coefficient? The predictor is for a linear regression. There's no reason why you can't compute a similar statistic based on, any kind of a regressor. Any questions? Okay, good. Yeah.
Just
Well, on this slide, if in fact there is a linear relationship between the thing, let's say that there really is a linear relationship, then the Pearson correlation is measuring exactly what it is. Okay? If there is a nonlinear relationship between things, okay, that something weird happens to people who are both old and tall, okay, then you would expect that there's a better predictor than just a linear regression, okay? But basically, this is an analogous statistic that you can use for any regression model to see how good it is. Yeah.
So the y minus f of x, that's the residual,
Right.
right? And the r that you're referring to, that's the correlation coefficient.
Okay, so here, notice that here, when I'm talking about r squared, I am not talking about a, notice, okay, on this slide, I am not talking about linear regression. I'm talking about any predictor f of x you have, right? On the previous slide, I was talking about linear regression, okay? Now, you may say the slide looks the same, and what the point here is that you could use this same kind of a statistic to judge the quality of any predictor. How much variance is it leaving unpredicted? That's kind of what this measure is telling you. And, you want that to be small, okay? The amount of variance left unpredicted. Any questions? Yes?
Would it be more fitting to use like the capital R squared because it's like so like for people instead of for energy, it's like as they use.
Okay, you're saying why do I have should I use a big R here instead of a little r?
Yeah, because like in the graph it uses the big R and then that takes away.
Okay, so if this bothers you, which is fine, send me mail and I'll try to change my little r's to big R's. Okay, but the principle is how much variance am I capturing is a good way to think about how good my classifier is. How much stuff remains unexplained, okay? And, by making it a ratio, it gives me a number that's easy to interpret. Okay, what else can I tell you? There's another way to interpret what a correlation coefficient means. And it is, remember last class there was some talk, I was talking to you about like eBay and doing suppose eBay could, you change the color of the background to green and it gives you $1 improvement every day. The question of, is a correlation you observe, is it represent a real relationship between the variables, or might it happen by chance? Okay? I mean, let's actually do a little experiment. Suppose I give you, 10 points. Okay? 1, 2, 3, up to 10. And I give you a random permutation of the y values. What is the chance that there is going to be a perfect correlation? Can anybody compute what that would be? What's the probability of the let's say I have people's height, I have people's weight. I randomly scramble their weights, I permute them. Okay? Should there now be a relationship between the permuted weights and the heights? No. What's the probability if I give you 10 of these people that in fact there is a perfect correlation? Is there any chance there could be what? Is there any chance there could be a perfect correlation? You're saying no? Okay. You guys haven't ever bet on things and be lucky. Okay? Or unlucky. 1 in what? 1 in 10? No, not 1 in 10. 1 in 10 factorial. There is some chance that there is going to be a perfect correlation. What is there? Is there a chance that there's going to be a 0.2 correlation? What's the probability of that? Well, it better be better, it's probably better than 1 in 10 factorial, right? So there is a separate question of, is my correlation that I'm observing real? Okay, does it really capture something? And, you know, you can imagine a world where you get a curve something like this, where if I see a correlation of, of a certain strength as a function of how many samples I have. There I had only 10 samples, right? What's the probability that if I had given people permuted weights and I had 1,000 people and I randomly permute them, what's the probability that there was a perfect correlation? Infinitely small, unless I did something dumb with my random permutation. That's probably more likely what happened. I probably didn't compute the random permutation. So what is the point? It should be the case that there should be some division between, as n gets larger, a smaller correlation is needed to be observed before you're going to take it as likely to be real. Okay? Does everybody kind of get that? So when we talk about statistical significance, okay, this is a function of, if I observe something, what is the number, what is the strength of the correlation, and what is the sample size? And usually you will measure significance in terms of what is the likely probability, what is the probability that it will be, that the chance of seeing this phenomena is small enough. What is the, I'd like to quantify it in terms of saying something is real if the chance of seeing, the odds of seeing this by chance is less than some threshold. Okay? The threshold is what they call the significance level, which in old statistics was always 0.05. Okay? Typically people today make it smaller because we have more data than we used to. Okay? But basically if you have a world of saying the chance of seeing this the odds of seeing this phenomena by chance is too small, therefore I'm going to believe it's real. The notion of what too small is the significance level. And for any significance level, there is going to be a boundary between below it, the correlation is too weak for me to really believe it with high confidence. And above it, then yes, this is probably not a fake, a spurious correlation. Any questions about that? So significance is going to be making the notion of whether it's real or not. Okay? Any questions? Yeah.
So do we want a correlation factor to be lesser than significance level or greater than that?
Do we want the correlation to be less than, or we want our correlation to be above this line here? Okay, this is the boundary where we will say above this, if I see this correlation, the odds that a correlation this strong would have happened by chance is small enough that I'm going to discount it. Maybe here it was 1 out of 20. Okay? If you really, really need it to be strong, you're going to bet your bottom, your last dollar on this. You probably want to have a stricter criteria, right? But once you specify the criteria threshold, recognize that there is going to be a division of this, where if I see a correlation this strong, okay, on this many points, it is probably not random chance. Okay? Any questions? Now, if I see a correlation of 0.15 on 250 points, can I use that 0.15 to make a good prediction of something? Well, it's a weak correlation. If it's a 0.15 correlation, how much of the variance does it explain? Something, well, okay, but 0.15 I can't do in my head, but 0.1 I can do in my head. What's the square of 0.1? 0.01. That would explain 1% of what's going on. Is being able to explain 1% of what's going on good? Well, it's better than being able to explain 0, but it's less than being able to explain more, right? Now, if I could have a large number of features, each of which explain 1%, and each one of which they are not correlated among themselves, they're independent things, maybe I could build a bigger classifier that could do much better, okay? But again, if all I have is are weak variables that are all very correlated with each other, I'm not going to be able to do a great job predicting it, even if it's a real phenomena, okay? There's some, it would not surprise me if there's a correlation between height and grades, okay? That the tallest people may earn better grades, slightly. Does that mean that, that I could predict somebody's grades from looking at them? Probably not, okay? But there may very well be something there, okay? Yeah.
And your note mentions that's the case for independent correlations, but in practice, like what is that ever the case? Like you want to determine weight based on height, and maybe height has say 5% contribution to variance, and then you have something like economic status, and that contributed another 5%. You wouldn't really be able to add that and say, oh.
Okay, so this is about the correlation thing. We said, again, get back to my thing. SAT score will predict your grades 0.42 correlation. Your parents' wealth will predict 0.47 your grades. If I have your grades and your SAT score and your parents' wealth, am I going to be able to do a good job of predicting your grades? I should be able to do better than with one of those variables, either one of those variables, but the degree of correlation between them is, if there's a lot of correlation between them, then I'm not going to learn much between the second variable, right? If there was perfect correlation between grades and between SAT scores and parents' money, and I now have your parents' money and your SAT score, okay, am I better off than just having the SAT score? No, okay, not for making predictions, okay? So again, our dream is, data scientists, we want to be able to have a large number of, variables that will help. Maybe the correlations are weak. If we have enough of them and they are independent, maybe we can do something more interesting. Any questions? Okay, so what is the purpose of significance testing? Okay, significance testing measures whether or not there is a real relationship as opposed to it being by chance. Okay, it doesn't measure whether the relationship is important. Okay, that's something we will call effect size. Okay, and if we looked at this graph, okay, this was a graph I got from someplace. They were measuring sleep of students, of people. They had a distribution for people at in the country. How much sleep did they get? They have a separate distribution of how much of a sleep does the average university student get? And it looks like there's a little shift. Is there a real difference between how much university students sleep and do university students really sleep less than people in the rest of the population? You say no? Well, you guys would know better than me, okay? But if it shows it's a function of how big is that shift and how many people are doing it, okay? How many people did they look at? If they talk to 5 students, they talk to 5 people outside the world, not an interesting statistic. Any questions? Okay, good. Now there are other ideas about correlation. Pearson correlation is a very good statistic. There is another correlation statistic that I find I like a lot, which is something called the Spearman rank correlation. What is the difference? The difference is it counts the number of disordered pairs between X and Y rather than than whether the data fits a line. Okay? Suppose I have, in this case, a correlation where this is X and this is Y and there was a strong correlation. If I compare this point, let's say 2 and 7, and this is going to be this value which was, let's say 17. What should be true about this value? Okay, the Y associated with this X. If there is a correlation, a positive relationship between the values of X and Y, if I take this pair, what should be true about this value? It should be bigger than 17, right? If this is height and weight, this person is taller than that person, this person should weigh more than that person. You could imagine taking every pair of points and now asking yourself, for every pair of X, how often does the relationship hold for the Y's? If there was if Y was randomly permuted, what would we expect, what fraction of the time would we expect that this value, the one with the larger X, is going to have the larger Y? Okay? Let's say this again. Suppose I randomly scrambled the weights. What's the probability in the scrambled weight that the bigger scrambled weight with an X, a bigger X is going to be bigger than the scrambled weight with the smaller X? Should be half the time, right? There's two possibilities. So you could imagine if there was an uncorrelated Y, half the time we would expect that for a given pair of rows, the one with the bigger X has the bigger Y. If they were perfectly correlated, we would expect that would be with probability 1, that's always going to happen. If they were negatively correlated perfectly, what should happen? This number should always be smaller than that number, right? So by counting the number of pairs that are not in the right order, we get a measure of the correlation, the agreement between X and Y. Does everybody agree with that? Now, why is this different than the Pearson correlation? Notice that this said something about Pearson correlation had something to do with lines fitting it, regression line fitting the data. Here we're just saying whether there is a positive relationship here. Look at these points. Let's say that we lived in a world where, in this case, if you have X less than Y, X less than 5, Y grows slowly with X. And then once you get greater than 5, Y grows very rapidly with X. Is there a relationship between Y and X here? There's certainly a very strong relationship. If I know X, I can predict Y. I can't do it with one regression line, right? I could do it with two regression lines. The right predictor is, is X greater than 5? If so, you're using the fast line. If it's less than it, you use the slow line. The Pearson correlation of this is defined by that regression line. The Pearson correlation was 0.69. Pretty good. But the Spearman correlation was 1. Does everybody see that? Here I have an example where the Pearson correlation and the Spearman correlation happen to agree, or be very closely agree at about 0.94. And here I have an example where I had a very strong relationship between X and Y, and one outlier point. Okay? Let's think what happens when you have one outlier point. Okay? The regression line is going to be trying to minimize the sum of squares error. Suppose this one outlier point gets pulled up to Mars. It gets pulled over here. What is going to happen to the regression line that best fits all of this data? It's going to shift up chasing this outlier point, right? So in fact, the further the outlier is, the worse the Pearson correlation is going to be. How will that outlier point affect the Spearman correlation? Well, it's kind of weird. In this case, the outlier point, first of all, it's big near the end. So there are very few pairs that are going to be ruined by moving this point out. Only the point's actually out here, right? And the further I move it out, does it have any effect on which pairs are kind of wrong? No, okay? So in this case, the Pearson correlation is substantially smaller than the Spearman correlation, and if I jack up that point, okay, for the outlier, the Pearson correlation will still say this is a good relationship. The Spearman correlation will eventually say that, the Pearson correlation will say it's bad, the Spearman correlation will say it's good. Any questions about that? Yes?
Is there a significance level for the Spearman correlation in the same way?
Is there a significance level? The answer is there should be, yes. Okay? Do I have that picture here in my head? No. But if you think about it, there's got to be something like that. There is some chance that you're going to get a correlation that is. Think about it. Let's take a. What are the chances you will have a perfect correlation between 2 points? A half, just 2 points. If I have 2 points, okay, then half the time I'm going to get perfect correlation, half the time am I impressed if I have 2 points and I've got a Spearman correlation of 1? I shouldn't be impressed, right? If I have 100 points, I have 1,000 points, I should start to be impressed. So yes, there's going to be a similar threshold going on there. The threshold's not going to be at exactly the same place, because I think Spearman correlations are by definition greater than or equal to the Pearson correlation. Okay? So, so it's not, the same thresholds don't apply, but clearly a threshold applies. Okay? Any question? Yeah?
In what case would the Spearman correlation be worse than the Pearson?
Well, when you say worse, in what case would it be worse? Now, suppose you want to really minimize the errors that you're getting, okay, in your predicting of something. Notice that notice first of all, when the Pearson correlation is associated with this linear model. So a Pearson correlation tells you how good a predictor you can build, right? It's less obvious that the Spearman correlation tells you how good a predictor you can build, right? You're trying to predict somebody's, let's say that there is in fact a perfect Spearman correlation between height and weight, okay? Let's say taller people in fact weigh more than people who are shorter than them, perfectly. Does that mean given your height, I can predict your weight? Well, there's not necessarily a linear relationship. There may be a nonlinear relationship. I don't know what that relationship is. I know that there is some kind of a monotonic relationship, but more than that I don't actually know. So Pearson correlation is good because it tells me how well am I predicting the thing I care about. Okay? Spearman correlation is telling me, look, There may be a nonlinear relationship that does a good job predicting it, as opposed to a linear relationship. Okay? Any questions? Yeah. That's a yeah.
In the first graph, where it increases after 5, right?
Yeah.
In that, why is the Spearman coefficient 1?
Why is the Spearman correlation 1? For any value, does everybody agree, if you look at this figure on the left, does everybody agree that if you have if you have 2 points, the one with the larger x has the larger y? Do you agree with that? So therefore, every pair of values, if you know x, you know that y, if you know the 2 x's and you know one of the y's, you know that other y has to be either greater than or less than it, right? And you're always going to get that right, okay? That's what the Spearman of 1 means. Any questions? Yes?
If in the last case, if the outliers comes earlier, near the beginning, would you change the Spearman coefficient?
Okay, so I have this outlier here. Where would it be bad for me for that outlier to be? If that outlier was the last point with the highest x, a high outlier means everything's perfect, right? Where would be the bad place for it? Okay, I guess the worst place for a high outlier would be where? Would it be in the middle to create the most out-of-order pairs? Or would it be all the way to the left? If I have my outlier, if the smallest value suddenly had the biggest weight, this is going to screw up every pair that involves that, right? It's going to screw up n of the n squared pairs. Okay? So where that outlier would be will affect the Pearson correlation. But the damage is still limited. If I raise this thing outlier, make it an incredibly high outlier, so long as it's bigger than the second biggest y, it no longer can cause more damage to the coefficient. Okay? Any questions? Okay. Now, how do you compute the Spearman correlation? Okay? One possibility is you try all pairs and you count. If I have n elements, how many pairs are there? Well, okay, I say n squared, big O-ish, there's n squared pairs. This would be a quadratic algorithm, right? In fact, there is another way to compute the Spearman correlation, where suppose we now replace the actual values, okay? You have x values and you've got y values. Suppose I replace the x values by the numbers 1 through n, telling about where that value appeared in the sorted order of the x's. And I replace the y values by the numbers 1 through n, depending upon where they fell in sorted order, right? If so, the rank of xi is going to be the position of xi in sorted order. Okay? Then you can compute the Spearman correlation in terms of the deviations in rank. What's the deviation between x sub I minus the deviation what's the rank of x sub I minus the rank of y sub I? If the Spearman correlation is going to be high, if the x value is third among the n values, you would like to make the most pairs work with it, you'd like the y associated with that to be third among the y's. Okay? If they're both third, the deviation is 0. Okay? So what is the Spearman correlation? It's 1 minus 6 over the sum of the squares of these deviations divided by n times n squared minus 1. Now this looks ghastly, right? But let's see if this makes sense. That's how I like to think about these things. Okay? What if there is a perfect Spearman correlation? What are the deviations going to be? There's no way, if there's no out of order pairs, then for every element, the ith highest x has to be mapped to the ith highest y. If not, there's an out of order, it has to be an out of order pair there. So if the deviations are 0, sum of 0 squared is 0, 1 minus 0 is 1, this makes sense, right? Now, what would we think the deviation should be, let's say in the case of randomness? Okay? Suppose we're dealing with a random thing, where these things were in permuted order. What would we think is the deviation, the expected deviation, if you have n values? Remember, we have n points. The x's are right, the y's have been scrambled. What do we think the expected value of di is going to be? Anyone have a guess? What? 1? You would expect that the difference between the rank of the x value and the y value would be 1? No, I don't believe that. And maybe I didn't make it clear. I have people's, let's put it this way. I've got people's class rank. Let's make something you understand, your class rank. And I have your GPA. And at most schools, it's, your class rank is a function of your GPA, right? Now suppose I randomly permute the GPAs. Okay? You ranked 63rd in your class. What do we think that your random permuted GPA should be? I don't know. What do you think the rank of it should be on average in expectation? Does anybody have any idea? You've got n points here. What? Okay, we're not communicating here. Okay? Let's say that we have two completely uncorrelated variables. Maybe that's what we're going to take a look at. Let's say we have your social security number and your real GPA. Let's try it like that. And your GPA. And what is the likelihood? Someone in here has the lowest social security number of anyone here. I don't know if you feel proud of that or not. Someone here has the highest one, right? Social security numbers by rank go between 1 and n. Now I take a look at your GPA, and I have people ranked by their GPA. What do the GPA ranks go between? What's the highest GPA rank and the lowest GPA rank? 1 and n. Okay? Now, if I have a student here whose social security number rank was 63, what do we think their expected GPA rank is going to be? Somebody with a hand. Yeah? n by 2 is what I would think, right? In principle, it seems like it should be something kind of like n by 2, right? It could be 1, it was equally likely to be 1 or n or 63. Now, what's the expected deviation then, if these were random? Okay, if there was no relationship between them ranks. What would the expected deviation be? It could be, it's not quite n by 2 for a reason, it's more subtle than that. Why? What about if you were number 1 in the class? What would be your expected deviation with this guy? Here you could be any one of the numbers equally likely. The difference is likely to be, it could be anyone from 1 to n, the average difference is going to be n over 2. Right? But what if you're in the middle of the class? What's this number going to be? It could be anywhere between 1 and n, but what's the biggest possible deviation? N by 2, right? So it's not going to be average n over 2, it's going to be something different. The bottom line, it works out to be 0, okay? Any questions about that? Now, why this weird stuff? I've still got a couple minutes, I'm going to finish this. Okay? Why is this weird relationship? Where does that come from? Can anybody see some reason why this comes from? Well, the average of, what you call it, what does the average sum of squares be? Okay, let's look at this. You guys know, I bet you, what is the sum, if I ask you guys, what is the sum as I goes from 1 to n of I? Does anybody know what that relationship is? You're going to say something like n plus 1 times n over 2, right? Something like that, right? Now, what is the sum as I goes from 1 to n of I squared? Does anybody know this? I bet somebody in here knows this. Or has anybody seen that? Someone who knows about it, yes. What is it?
N into n plus 1 into 2 plus 1.
Say that again more slowly. N
Into n plus 1 into 2n plus 1.
n times n plus 1 times, what was it? 2n plus 1 divided by what? 2? 6. Okay? Has anybody ever seen this thing before? Now, what does this thing look like? Do you see a 6? Do you see an n? Do you see n? What does n squared come out to? Isn't that n squared minus 1? Isn't that n plus 1 times n minus 1? Does everybody see that this normalizing factor is kind of like this, basically twice or a half what you see there? Notice that there's a 2 here that we didn't have. That's where the twice is coming here. So basically this is saying what's the sum of squares difference over what amounts to essentially the average, what you would expect from the sum of squares if it was, kind of completely maximized, okay? Any questions about that? Okay? Anyway, this gives you a way to compute the Spearman correlation. Any questions? Any other questions? I've got 1 minute. I'd love there to be one question, so I'm not tempted to introduce a new topic. Okay? Okay, anyway, I'll let you go. For a minute, I'll let you go. Spend that minute on the next homework assignment and get going on that. And we will, yes, question?
So you said when it's random, the deviation is 0.
Yeah.
So then,
No, when I said it was random, you would expect the Spearman correlation to be 0, which would mean you would want this to be 1/2, right? You would want this term to be equal to 1. Then it's 1 minus 1. And this says the sum of the squares of those deviations is roughly half of what you would expect from that. And that's kind of where it's coming from. Okay, thank you.